Okay, that's fine. So, as for the last session which we have discussed, and we'll continue with our content, and this session is basically on the design aspect of subsystem. So that we'll discuss in this session, that how the design of subsystem is implemented. So basically, when we talk about the function of chip, so the chip function is generally can be divided into many categories. Okay, but the main categories which we are dealing with is actually data patch operators. Okay, data patch operators, or memory elements, or control structures, or special purpose cells. That includes our input output, power distribution, clock generation, and distribution, and analog and RF, that is radio frequency. Okay. So these are actually, we can say, the categories where generally the division has been made as far as C function is concerned. The C function is generally divided into this category. So they are data patch operators, memory element, and control structures, and some special purposes like input output, power distribution, clock generation, distribution, and analog and radio frequency. Now, as we are dealing with CMOS systems, right? That complementary metal oxide semiconductor. So this CMOS system design basically consists of partitioning of the systems into subsystems of the types that is actually that we have discussed just now. That means that database operator, memory element, control structure, and with some special purpose cells like input output, power distribution, clock generation, analog RF, etc., etc. Okay, so basically this CMOS system design consists of partitioning of the system into subsystem, which we have discussed just recently. So many options that exist that make trade-off between speed, density, or we can say programmability, ease of design, and other variables. Okay. So that is many important. So one part is that whatever the options which we have that make a trade-off between speed, density, ease of design, programmability, and other variables. So common database operators, if you can consider, that includes actually, so what are they? So they are adders, non one or zero detectors, comparators, counters, Boolean logic units, you can say error correcting code blocks, shifters, and multipliers. So these are actually common database operators that mainly adders, 1-0 detectors, comparator, counters, Boolean logic units, shifters, and multipliers, like this. Okay. So I hope you can able to understand that what actually this common database is all about and how it is considered. Now, this is when we consider it. So, addition form of basic of many processing operations. That is from arithmetic logic unit to address generation of to multiplication to filtering. Okay. Now, other circuit that are two binary numbers are of great interest in recent times to digital system design. So utmost care has been taken, that means in extensive way, that the added architecture that serve different speed or power or area requirement. Now in this session, we'll discuss about the with half adder and full adder for single bit addition. Okay, and then we'll discuss about the consideration of CPA. CPA means this carry programmed adders that we call it for the addition of multi-bit words. Okay, and finally, related to structures such as subtractor and multiple input adders, we can discuss. Okay, this single bit addition, if you can see the half order, you can see here in this figure, it's 11.11a. This, if you can see this figure, so that adds actually two single bit inputs. Okay, this is one input A, another input B. Okay, so as you know, half order we have a sum and there is a carry, right? So which is carry out, C out that we call it. And so this is actually the half adder. So this half adder that we see here, that adds two single bit inputs, that is A and B, and the result is 0, 1 or 2. So the two bits are required to represent the value, uh, and they are called sum and carry out. Okay, so this is actually two inputs. So as we know, this is one is sum and another is carry out. That we call it C out also. Okay, in abbreviate we call it C out. Now the carry out is equivalent to the carry in to the next more significant column of the multi-bit adder. Okay, this carry out is equivalent to carry in to the next more significant column of a multi-bit adder. So it can be described as having double the weight of the other bits. Okay. If multiple adders are to be cascaded, then each must be able to receive the carry in. Okay, such a full adder we can see here, that is shown here in this figure. So this one input A, another input B. So this is the sum S, and this is carry out, and this another C is basically the third input called C or C in. Okay, this is a C or C in, that is called another input. Okay, so if you can see the truth table, so this is actually the truth table of half adder and full adder. So as you can see here, so we have two inputs A and B, and this A B can take the value 0, 0, 0, 1, 1, 0, 1, 1. Okay, so if you can take the sum, so 0, 0, 0, so out this C out will be 0 and sum will be 0. 0, 1, the C out will be 0 and sum will be 1. So this S is actually our sum, and C out is actually a carry out. Okay, so what is the carry out? Similarly, 1, 0, if we take into consideration, so 1, if A is equal to 1 and B is equal to 0, then the sum will be 1 and the carry output, that is C out, will be 0. But if it is 1, 1, that means the input A is 1 and input B is 1, then the sum will be 0 and the output will be 1. Because 1, 1, so sum will be 0 and the carry will be taken into consideration. So that is 1. So this is the truth table of half adder. Similarly, the truth table of full adder, if we take into consideration, so A, B, all the four combination we have to is generally taken. So that is 0, 0, 0, 1, 1, 0, 1, 1. Just like we take the combination of two inputs A and B. Like so, here also the same two combination we have to take for two inputs. Along with this, the extra input is also given. So just a just a minute, everyone. Ashok. Hi, Ashok. Yeah, Ashok. Yeah. No, 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 Ashok. Actually, I'm in the department and I'm taking the class now. Oh, sure, 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 sure. Maybe after 4 p.m. Then we can wait. We can meet then. Oh, sure, sure, Ashok. Then we can meet then. Okay, 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 Ashok. Okay, see you then. Okay, so what we have discussed so far, so if you take into consideration of the truth table, so this truth table of half order is very clear. So we have two inputs and four combination has been taken, and we have sum and C out. So as per this one, the figure which you have seen here, that this is the sum and this is the carry out. Okay, but in full adder actually. the full adder is something that we have a third input that we call C or Cin also. So the truth table, uh, as you can see here, this is the truth table of half adder. Okay. Now for full adder, it is sometimes useful to define generate that we generally call G or propagate P. Okay, and kill K signals. Okay. So there are three terminology we have to use. One is G, P, and K. Generate, propagate, and kill. Okay. Now the adder generates a carry when C out is true independent of C in. Okay. The C output, that is the carry output, is true independent of C in. C in is the another third input that we have discussed. So G is equal to A dot B, that is the multiplication A dot B, that is the AND operation. Okay. Now adder kills a carry when C out, that is the carry out is false independent of this third input C in. Okay. So this K that we call kill is basically the dot AND operation of A complement B complement. So if A is one input and B is another input, so the AND operation will be A complement dot B complement. Okay, so that actually K. So K is equal to A complement dot B complement, which is nothing but A plus B bar. So this is nothing but our De Morgan's law, right? Which we have just studied in our previous classes. So this is our De Morgan's law. So the adder that propagates a carry, that produces a carry out if and only if it receives a carry in when exact one input is true. So this P is actually P XOR P, A XOR P. So that actually the case. Okay. So this is actually the uh, the details about a full adder. So if you take into consideration this truth table, so as you know, this G is generate, P is propagate, and then K will be kill. Okay. So accordingly, as we have two inputs, which we have A and B, and there are four combinations can be possible: 0, 0, 0, 1, 1, 0, 1, 1, and this extra third input that we can see or see in. So it can be 0, 1, or it can here also 0, 1, 0, 1, and 0, 1 like this, and G and P and K will be 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0. Okay. So all the combinations of it will be taken. So accordingly, if you can find out its carry and sum, so it will be come out to be for A and B 0, and let's say for 0. So the C out will be 0 and sum will be 0, right? Similarly, for 0, 0, the let's say the third input 1, and G and P, G will be 0, P will be 0, and K will be 1. So in that cases, if this part will be taken into consideration, then C out will be 0, and that means carry out will be 0 and sum will be 1. Similarly, for this uh, another combination of two inputs A and B, if we take 0 and 1, then and if the C input will be 0, and let's say our generate will be 0, propagation will be 1, kill will be 0, then our C out will be 0, and sum will be 1. Similarly, the inputs A and B is 0 and 1, but in these cases, if our in other third input, if it is 1, then and for and G will be 0, P will be 1, and K will be 0, then in that cases, C out will be 1, and sum will be 0. Similarly, if third combination of two inputs will be taken as 1 and 0, that means A is 1 and B is 0, then the carry will be 0, uh, G will be 0, P will be 1, K will be 0. If this is the case, for C is equal to 0, if and for C is equal to, if for C is equal to 0, if G is equal to 0, P is equal to 1, and K is equal to 0, then our carry output will be 1 and sum will be 0. Similarly, for both for the input A and B, if A is equal to 1, B is equal to 0, and C will be 1, then for G is equal to 0, P is equal to 1, and K is equal to 0, then C out will be 1, and S will be 0. Similarly, the last combination, which is A and B, is the last combination of both the inputs A and B. If it is 1 1, that means A is 1, B is 1, and this carry will be 0. If in the case of carry is 0 and G is equal to 1, propagation will be 0, that will be 0, and kill, that is K is equal to 0, then the C out will be 1, that is carry will be 1, and sum will be 0. Okay, and the last combination, that for both the inputs, that if A is equal to 1, B is equal to 1, and if the C will be 1, okay, if C will be 1, then then if G is equal to 1, P is equal to 0, and K is equal to 0. Okay, so in that cases, our the carry output will be 1 and sum will be 1. So this is actually the truth table of full adder. Okay, now from the truth table, the half adder logic can be implemented like this. Sum will be A XOR B, and C out will be AND operation of A and B. C out will be A and B, sum and carry out. Okay, so this is actually our half adder. This A that is we seen here. This is our half adder, and this is actually our full adder. Okay. So in whether it is half adder and full adder, so two single bit inputs A and B is common. Okay, so the only difference between full adder and a half adder is that here this in case of full adder, that is the third input, that we call it C or C in here. Okay. So just once again, I am giving a synopsis here, that means to give a brief idea. So in half adder, we have two single inputs A and B, and the result is 0 or 1 or 2. So two bits are equivalent to represent the value, and they are called sum and carry out. Now the carry out is equivalent to it carry in to the next most significant column of a multi-bit adder. So it can be described as having a double the weight of the other bits. If multiple adder has to be cascaded, then it must be able to receive the carry in. So this full adder that we are seeing here, that in this figure, so this is a third input that we call C or C in. Okay. Now this is the truth table of half adder which we have just now discussed, and for full adder there are three main consideration we have to take. So that generally defined to be: one is generate, P is propagate, and K is kill signal. So these are three another signals we have to incorporate. So the adder actually generates the carry when C out is true independent of C in. Okay, and in that cases our G. So when we G operation is taking place, so this G operation, sorry, this G operation is nothing but A dot B. That is AND operation between A and B. Now the adder kills a carry when C out. Actually, the carry out is false and independent of C in. So this carry, what you can say, this carry will be, sorry, the skill will be K. Is the actually A plus B complement. Okay, so this is a NOR operation, A plus B complement. So which is nothing but, as per De Morgan's law, it will be A complement dot B complement. So that means A complement and B complement. Okay, so this is actually our uh, our key. And what is propagate? Propagation. The P is nothing but A XOR B. So the adder propagates a carry, that is, it produces a carry out if and only if it receives a carry in when exactly one input is true. So this propagate will be A XOR B. Okay. So this is K. This is G. So G is A dot B, that is AND operation between A and B. This K operation is basically the NOR operation, that is A plus B complement, or you can say like this, it is the AND operation between A complement and B complement, and this propagate is equal to the XOR between A and B. So based on this, this truth table is of full adder is defined. Okay. So the combination of A and B the same as the half adder. So we will take 0, 0, 0, 1, 1, 0, 1, 1. The only thing is that the third input which we are taking C here in full adder C. So this C can be any combination. It can be 0 or 1. So accordingly, for each combination of A and B, so the C input is added. So it can be for A and B 0, 0, the C can be 0, 1. Similarly for A and B 0, 1, the C will be 0, 1. If A and B is 1, 0, so C will be 0, 1. If A and B is 1, 1, C will be 0, 1. Now G and P, the you know what is G here? G is, I already mentioned, G is equal to with the AND operation between A and B, whereas K will be A plus B complement. That is the NOR operation between A and B. And what is P? P is the XOR operation between A and B. So G is the generate, P is the propagate, and K is the key. Okay. So this way we have to define GPK, and accordingly, whatever the G and P and K value we will get, so we'll get the C out, and that is carry out, and some accordingly. Okay. So half order logic, if we take into consideration the, so from the truth table, we can easily can conclude that the sum will be is nothing but sum will be XOR operation between two inputs A and B, whereas the carry out, the C out, will be AND operation between A and B. Okay, A dot B and A, that is C out, and A XOR B will be sum. Now, if you take into consideration of this full adder logic, so full adder logic, how we can define in terms of sum and carry out. So it is like uh, A B complement C complement plus A complement B C complement plus A complement B complement C plus A B C. Okay. So if we can define in terms of XOR operation, so it will be A XOR B whole bracket XOR C. So this A XOR B is nothing but propagate, that is B XOR C. Okay. So this is the full adder logic. So when we define sum, so this will be defined like this. So it will be A B complement C complement plus A complement B C complement plus A complement B complement C plus A B C. Okay. Now we can just generalize way if we just define in terms of XOR operation. So it will be A XOR B XOR C. Okay. Now A XOR B is nothing but propagate, that is P. Okay. The P XOR C. So this is actually sum. Now after sum, we will define C out for full adder. So this carry out will be AB, that is AND operation between A and B, plus AC, that is AND operation between A and C, plus BC, that is AND operation between B and C. Okay. Now we can just rearrange the things. So it is AB plus C. We take C common, so it will be A plus B. Okay. Now we can further rearrange the thing. So this can be A complement B complement plus C complement whole bracket A complement plus B complement, then whole complement. Okay. So this is a whole complement of A complement B complement plus C complement whole bracket A complement plus B. Okay. Now this is actually this carry the C, this carry gate which we just now defined. So that is also called majority gate. Okay. So that we generally abbreviate as MAJ. That's majority gate of the A, B, and C, the three inputs A, B, and C. Okay. So this majority gate A, B, and C is nothing but AB plus AC plus BC. Okay. And if we can rearrange this way, we can rearrange like AB plus C. C if we take into common, it will be A plus B. Then A complement, B complement plus C complement, A complement plus B complement, total 4 complement. Okay, so this actually our this carry gate is called majority gate. Okay, and why it is called majority gate? Because it produces a 1 if at least 2 of the 3 inputs are 1. You got my point. If it is called majority gate because it produces a 1 if at least 2 of the 3 inputs is 1. That is why uh, it is called majority gate. Okay, so the straightforward way, that means you can say the straightforward approach to design a adder with logic gates. If you can see, this is the figure of half adder design. Okay, so this is XOR operation. So that is between two inputs A and B. This is sum, and this is the AND operation. So that is between two inputs A and B. So this XOR operation, which is between two inputs A and B, the output is sum. Whereas the AND operation, which we are seeing here, within two inputs A and B, the output will be carry out. That we call it also C out also. Okay. Now, full adders are used most often, so they will receive uh, uh, much attention in as far as digital electronics or CMOS VLSI is concerned. Okay. Now, if you take into consideration of inverter operation, so this is this, if the input is A, then the output will be A in A complement. So this is the output. So let it be the input, the output would be B complement. If C the input, the C will be uh, this C complement. C the input and output will be C complement. So this is actually our full adder circuit. If you can see here, so this is a full adder. So one is the sum. Sum is nothing but as we have seen here. So this is actually the XOR operation. Some will be XOR operation A, B, C, which we have seen here. So A, B complement, C complement plus A complement plus B, C complement plus A complement, B complement, C plus APC. So A complement B, whole bracket complement C, XOR C. So A complement B is nothing but our XOR operation between two inputs. So that is we denote as P. So P XOR C. So this S is nothing but the XOR operation between A, B, and C. And carry out, as you define that this is a majority gate. So that is majority gate between A, B, and C. So this is our carry out. Okay. So like this way. So this full adder symbol can be written. But in terms of design concept, if we take into consideration of PMOS and NMOS, okay, the PMOS and NMOS. So this is the design for full adder. It's a design for full adder. This is for sum, and this is for carry out. Okay. So how we can do this one? So we have to do the CMOS and the NMOS logic accordingly. Okay, the bubble, as that you can see here, the bubble structure with the this transistor is the this PMOS, and there is no bubble, that is NMOS. So here, if you can see, this is A, and this is the PMOS, and this is A complement, which is another PMOS. So that is connected in parallel, and this is B, this is and this is another um, B complement, and this is B, and this is another B complement. So this is another two PMOS. So if you can see here, they are connected like this. Okay, so this is connected like this. Similarly for C and C, another input, we have another PMOS here, and C complement, this is another PMOS, and here also there is another, here NMOS. C is NMOS here, and this is another NMOS here. So C and C complement, and this is B, this is another input B, and this is another input B for this NMOS. And what are the output we are getting from here in this NMOS, and in this NMOS it will be complement, and they're connected here. Okay. Similarly, this is for another for A and A complement. Okay. So this is for NMOS, and it is grounded here. So here we will take the output, and this is actually a sum. So this is for actually full adder design as far as when we design it with the NMOS and PMOS. Similarly, if in full adder, the another after sum, it will be another output will be this carry out. Okay, so if you can see here, this a this PMOS A complement, B complement, and B complement. So this all are connected in this fashion. So these are all in parallel, and whatever again this A complement and C complement, these are also in parallel, and this one A complement C complement parallel. These are actually NMOS here. Sorry, this is actually NMOS here. Whereas this one is actually a PMOS. Okay. Similarly, B and B complement, if we can see here, this is also parallelly connected along with the A complement. So from here, actually, we take the output. So that is actually C out. Okay. So this is the way how the full adder is designed using NMOS and PMOS. Okay. Now the full adder of figure that we can see here, B, is employed actually 32 transistors, 6 for inverter and 10 for majority gate, and 16 for 3 input XOR gate. Okay, if you can see in this figure B, so there are total 32 transistors. So 6 for inverter, 10 for majority gate, and 16 for 3 input XOR. But a more compact design is based on the observation S can be focused into reuse of C outcomes. So it's nothing but S is equal to A, B, C, that is AND operation between the three inputs A, B, and C, plus that is our OR operation, whole bracket A, B, and C, that is OR operation among the three inputs A, B, and C, uh, and C out complement. That is the AND operation between the three inputs A, B, and C, which is the OR operation, and the C out. So this is actually full adder design. So if in the questions, if it is asked the full adder design and half adder design, then you have to explain like this. Explain with the description along with the uh, right truth table along with the design part. The design within CMOS here. Okay. So how the different NMOS and PMOS are connected in different fashions, which are in parallel, which are in series. So this way. So in full ladder circuit, we have a sum and that will be carry. So for sum, this one this way we have to design the circuit, whereas for carry out, we have to design the carry like that. Okay. Now, this is actually our full adder for carry refill operation. Okay, this is actually full adder carry refill operation. So, so if you can see here, the design which is shown at the gate A and transistor B level 11.4. You can see here 11.4 and uses only 28 transistor here. So here actually it uses 28 actually transistors. Now, if you can note that the PMOS network is very identical to the NMOS network rather than being conduction complement is concerned. So the topology is called minor adder. Okay. Now this simplification reduces the number of series transistors and make the layout more uniform. Now it can be also possible because of the addition function is symmetry. That is the function of complement inputs is the complement of the function. Now the mirror adder has a greater delay to the compute S than C out. That is sum and then the C out. Now in carry ripple adders, which you can see the critical path goes from C to C out through many full adder. So the extra delay computing S is very not that much important. So it is unimportant. So we can see 11.4 C here in this figure, 11.4 C. The adder with transistor sizes optimized to favor the critical path using the number of techniques. Okay, so that is very important. So feed the carry in signal C to the inner input. So the internal capacitance is already discharged. Now, we have to make all the transistors in the sum logic where gate signals are connected to the carry in and carry logic minimize size. That is 1 in, that is 4 lambda. Now, this minimizes the branching effort on the critical part. Now, keep routing on the signal as short as possible to reduce the interconnect capacity. Then we have to determine the width of series transistor by logical effort and simulation. And we have to build an asymmetric gate that reduces the logical effort from C to C out at the expense of effort to S. Okay. So this is actually, so anyway, this is for your only for reference only full adder for carry ripple operation. But the main consideration is that you have to know and study and design well with respect to half adder and full adder design, especially full adder design, how with the CMOS logic. Okay. So how the full adder is designed, PMOS and NMOS, as you can see here. Okay. So you do like this. So that is very important. So you should know the design part along with the full adder truth table and its description and design. Yeah. So, so far we have studied about the subsystem design system and how this the function is generally divided into different categories and also we have discussed that how the CMOS system design are different in the which is partition in different type of types which we generally categorize as data path operator, memory elements, control structure, special purpose cells that includes our input output, power distribution, clock generation and distribution, analog and RF. Okay. Now, so then we discussed about that how the single bit addition is taken into place. First, we discussed about half adder and the half what is the logic of half adder and what is the truth table of half adder. Then we discussed about full adder uh, uh, and full adder and then full adder. What is the truth table for that one and how to design full adder using CMOS. That is how the PMOS and NMOS are connected together to form the full adder. So we have a sum and another is carry. So for this is for sum. This one if you can see here, this is for sum, the full adder design of sum, and this is the for full adder design for carry. Okay, so S is the sum, C is the carry output. So we have to go it. And this is the symbol actually. Okay. So this is actually sum. That means this is the XOR operation between the three inputs A, B, C, and and this is actually our majority. That this is called majority uh, the full adder at the gate A and transistor B levels. So because it produces the majority gate, it is called because the carry gate is also called majority gate because it produces one if at least two of the three inputs are one. Okay, so that is why the carry gate is also called majority gate. Okay, so this carry gate is nothing but majority gate. So that generally it is abbreviated as MAJ. Okay, so this is for sum and this is for carry, and this is for this how to notify the sum and carry. Okay, and this is for full adder for carry ripple operation is for your reference only. So how this can be done with the ripple operation, so that actually the circuit diagram and design accordingly. And just already we have discussed about this device characterization part. So generally, this we generally deal with the electron microscopy analysis. So in these cases, we are mostly focusing on electron microscopy. So electron microscopy, as I already discussed, the electron has actually very high energy, and because of high energy, we can able to tune the wavelength because the electron has high energy, so we can able to tune the wavelength accordingly. And as we can tune the wavelength, so the resolution can be improved in accordance with. Okay, as we have already discussed in our offline classes that how the wavelength and the resolutions are interrelated with each other, and it all depends upon this how the electron energy and how what is the accelerating potential of the electron energy, so that will be very important to make the characterization. So it all come with the phenomenon of electrons, which we generally talk about. So just it is a just a revision of what we have studied so far in the electron microscopy study. So, so that I am again describing it so that it will be clear to you that how the characterization is important when we make any devices. Okay, because when we make any devices, we should know that how our devices looks like. So for that, we need to use some electromagnetic radiation. Previously, it was used like UV light or photon energy, but thing is that the photon energy is not sufficient enough to to resolve the aspect ratio the devices that we have made. So in that cases, we need to have some extra energy, so where the wavelength will be very smaller, so that so that the resolution can be improved. Now the wavelength can be reduced if we can use sufficient energy, and in that cases our electron energy will be a great support, because as we can increase the electron energy, we can able to reduce the wavelength, and as we can reduce the wavelength, we can improve the uh, resolution. Okay. This is actually a typical electron microscope. So if you can see here, this is actually the electron microscope here, and somewhere the electron gun is here at the top of it, and there is a what we can say the electrons are emitted, and this is actually finally uh, interact with our samples, and then some interaction will take place, and depending upon what kind of we are microscopy we are using, and there are different types of signals are generated as far as electrons are interact with our samples. Many with the interaction of electrons with our samples, many signals are actually generated, like X-ray, like Auger electrons. Some are secondary electrons, some are backscattered electrons, and some are actually transmitted electrons. Okay. Now, what about the electrons that we are using for morphological analysis in the TM, that is transmission electron microscope? So that is actually that transmitted electrons we take into consideration, and this is actually our elastic electrons. Why it is called elastic electrons? Because the electrons, which is after interacting with the samples, so the energy remains same. It means whatever the energy of the electron before interaction and after the interaction, then the energy will be same. So that is why this is called elastic electrons. So that kind of electrons is basically used in the transmission electron microscope, and the typical oscillating voltage is minimum 100 kilovolt. Because that is the minimum requirement. Somewhere, if you can see, the electron gun has oscillating potential up to 400 kV. Okay, so that is also quite possible. Now, so the image formation that generally is done by this transmission electron microscope with the help of this high energy electron beam. Along with the morphological analysis, we can able to get some data as far as that we call it diffraction data. So that it can be obtained from the image area. Okay, and so this is actually the when we discuss about this electron microscope, we can able to resolve our the specimens accordingly, because here due to high energy electron beam, it is so high that we can able to get the resolution up to even less than 0.5 nanometer also. Okay, so 0.5 nanometer to the resolutions we can able to attain. So if any devices which we have, let's say we have a transistor which we are making, let's say in the realm of, let's say, less than 5 nanometer, even 10 nanometer devices. Now we can able to achieve channel length up to 2 nanometer, 3 nanometer. So that we can able to see with this sophisticated electron instrument that we call transmission electron microscope. Now, this mainly that why it is possible with this an instrument is that it is specifically accompanied with many accessories and parts which make it possible to see our samples accordingly. So one is that we have our electron gun here. So that depending upon the electron gun is accompanied with what accelerating potential. So this TM is basically minimum is 100 kb electron gun is used. Apart from this, we have a sophisticated condenser systems where the lenses and apertures for controlling illumination on the sample, and specimen chamber assembly which we have in these cases, along also the objective lens system, that is image forming lens and limit resolution and aperture control imaging conditions here. Okay, and then after that we have a projector lens system that magnifies the image or diffraction pattern onto the final scale. Okay, so through a, electromagnetic lens system, we can able to tune the electron beam and can be able to focus on our samples uh, correctly. So that helps us to take the samples image correctly. So this is actually our typical system, and if you can see the electron gun that we call it electron emitter or cathode, so this is like hairpin kind of structure. Okay, if you can see here, this is a hairpin kind of structure. So it's very, and the beam diameter of this electron gun is maybe less than 1 nanometer. So this is actually so it is so you can say so small and so thin, and you can say the hairpin structure here, like kind of thing. And the beam diameter is coming out to be considered to be 1 nanometer somewhere. Then we have a positive electrode, so that we call anode, and some condenser lens, condenser aperture. Then specimen here, where we are having our specimen, and this is our objective lens. Now diffraction beam, that is objective back focal plane also plane of diffraction pattern and of the objective aperture diaphragm, so which are 20 or 50 micrometer. And single stage magnified image, also plane of selector aperture diaphragm, that is actually 10 to 50 micrometer. Now, in a two-stage magnified image, in B, diffraction pattern image in one stage and also plane of the intermediate stage. And this is our projective lens. Yeah, this is our projective lens. And in A, the three-stage magnified image, in B, two-stage magnified diffraction pattern, in the final screen of photographic plate respectively. Okay. So this is actually the schematics of the transmission electron microscope, and this is actually how our samples can be screened, can be shown. This is some of the examples actually. So where we can able to resolve our samples. If you can see this image, so this is our scale bar. So this is our 100 nanometer scale bar we are using here, and we can able to see our samples very clearly. You can see here that within that 100 nanometer how a samples looks like, and how this different grain boundaries we can able to see here. Okay, so this is a very clear picture with the help of electron beam, and this is only possible with the help of this transmission electron microscope. So this is a very a nice way to characterize any of our samples with the help of transmission electron microscope. Let's say we have a precipitates in an alloy, so we can able to also see in the this instruments very clearly. Okay, so this is also very important. Similarly, we have a precipitated particles on the silicon. Let's say we have a silica or silicon dioxide precipitated particle on silicon substrate. Okay, so we can see the here the silicon substrate, how this silicon substrate precipitated particle is on the silicon. If we can have a dislocations in a alloy structure, we can able to see clearly in the electron microscope. So this is a very so this is a very nice way, and the advantage of using uh, this microscopy tool, especially this electron microscopy tool, to examine our objects and to characterize in that regard. Similarly, this is another structure where we have a lamellar precipitate on the stainless steel. Okay. So this is also can be possible. So we can able to see the images very clearly with the help of electron beam images. Okay, and this is actually our electron diffraction pattern, where we can able to check what are actually different planes are oriented in which way, so we can able to see. So there are two ways of there are different ways of specimen preparation, and specimen preparation actually is a difficult task in transmission electron microscope. And generally, we are taking the samples like slices, like films, or powder, or fragments, or foils, or replicas type of thing. Okay, so it has to be very very small, very very thin sample. Um, so we have to take a very thin sample. But if it is not thin enough, then we have to make it thin enough by ultra microtomy. That is that is a procedure. It's called ultra microtomy, where we can crush and disperse on a carbon film. So this is actually the way of making specimen preparation. Similarly, for foils, 3 mm diameter disc is given, and it's very very thin. The foils, that is 0.1 to 1 micrometer, depends on the materials and voltage. Okay, so it's very important that we have a ultra microscope. If you need to prepare the samples for characterize or in the this transmission electron microscope, we have to take our samples accurately, because the specimen preparation is very very important. If it is not thin enough, we have to make it thin enough by ultramicrotomy. Okay, and the samples can be taken in different form. It can be films, it can be slices, It can be fragments, it can be powders, it can be replicas, or it can be foils, anything. And the foils and the this foils actually, as I have mentioned, this 3 millimeter diameter disc, and it's very thin, 0.1 to 1 micrometer, depending on the material and voltage. And we have to make it by mechanical thinning, chemical thinning, or iron milling process. Okay. This is okay. This is uh, this is actually very important that whatever the times we can do for the lattice imaging, or it can be used for many diffracted beam, and can be used for slight of focus, need very thin specimen region, and need precise specimen alignment. Because you can see here, this you can able to see the atoms here, and this is one example where the high resolution electron microscope of this cubic phase with incident electron beam parallel to this plane 100 plane, which so this way can be seen here. Okay. So we can able to see the orientation of the atoms, how the planes are oriented in which way. So we can able to see also in this TM. And we can able to usually image the simulate to determine the feature of the structure. So channels through foil or channels maybe can be light or dark in image, so that we can able to see. Okay. So this is different types of this diffraction data also we can able to generate. So it, where we can get to know what kind of orientations are there in different planes and different phases. We can also determine. So likewise, we can able to do. This is actually our bright field imaging. Only main beam is used, and aperture in back focal plane blocks the diffraction beam. And the image construct is mainly due to subtraction of intensity from the main beam by diffraction. Okay. Now bright field imaging. So this is the way how we can able to see the images. Also, we can able to see the dislocation image construct due to subtraction of intensity from the main beam diffraction. So this is actually examples of dislocation. Now, if you can see here the incident beam, we have either we have a lower mass or higher mass. We have the objective lens, objective aperture, and this image plane, and this is the intensity profile. So difference in diffraction contrast, that some planes diffract more stronger than others. So defects may affect the diffraction. So mass thickness, contrast, or absorption scattering thicker area and materials are higher Z are actually the atomic number with higher atomic number it will be dark actually. And this is the way where you can see the this diffraction pattern. This is also called the selected area independent diffraction pattern. So we can able to see this different with HKL planes. So we can able to see the planes and determine the planes accordingly. So basically, this one is helpful to have some idea what phases are present, and d value, the interplanar distance. Also, we can able to determine, and systematic absence of lattice centering. Then also can be determined, and the intensity. But the intensity information is actually difficult to interpret. So yeah, so this is all about. Okay. But many important thing is that when you have a preparation of the sample. So that is very important because when you do any sample preparation, we need to do to we need to do with the thin samples only. But if it is not thin enough, we have to do it by ultra microchromic process by crushing or disperse on the carbon film. But we have to note it that whatever the sample preparation or specimen preparation we have to do, we have to take it as powder or fragments or like slices or films or foils like this kind of thing we have to make it. And foils which we generally take into consideration, that is generally 3 millimeter diameter disc and very very thin, that is around 0.1 micron size depending upon the material and voltage. And this foils, which is 3 millimeter dice, is very thin, and the specimen preparation is made by mechanical thinning, that we call grinding, or chemical etching or thinning, that we call etching process also, and iron milling also, that we also call sputtering. So this is all thing about how the characterization of the samples is done by transmission electron microscope. In our cases, whatever the in our samples which we prepare, that means in our cases we are making our devices that we also. So the devices also can be made by this lithography techniques, and mostly the use of electron beam, which we call electron beam lithography. Then using this electron beam energy, whatever the device we have fabricated, we can able to analyze and can be able to characterize with the help of this transmission electron microscope. So this is the analysis we can able to make it by this way. Okay. Okay, fine. So, just a small announcement to all of you that this Saturday, I will conduct one quiz exam. So that I will post it in the Moodle. So some set of questions will be asked. So you please uh, uh, okay, you give the answer of each questions and submit in that date. Okay, I will give you the timeline, and you prepare the uh, you send me the answers accordingly in the Moodle platform. Okay, so this Saturday will be the this quiz answers. Maybe I'm planning from Friday evening to Saturday evening. So 1 day time I will give, so you can complete your quiz accordingly. Okay. So, so that is one announcement. And next class we will have our class as per our time. So 9 a.m. in the morning and 3 p.m. in the afternoon session. Okay. So we'll also discuss some of our contents as far as this VLSI system design is concerned, and we can continue accordingly. Okay. So okay then. So with this, we'll conclude our today's class. So we'll meet on Friday at 9 a.m. Okay. But one announcement: Saturday we'll have Saturday. I'm planning from Friday evening to Saturday evening. This 1 day time. Before that, I will put the questions in the Moodle platform, so we can have the questions. So you can answer the questions accordingly. Okay. Anyway, I will share the details in your in the in the group so that you can get to it. Okay. So with this, we'll conclude our session. So you may leave the session now.